here. I think this should be good to go. Okay. All right. So welcome one last time as we're facing AP Calculus. Again, the test is coming up on Monday. So this really is going to be our very last AP Calculus exam run through. Again, that test is on Monday. So hopefully those who are following along are going through this as well. I know there are a lot of people that might be cramming right before the exam itself. But nonetheless, this will be the last time that we'll be doing this for this year. We might be returning to this subject next year as we transition out into our summer session of study. But we have the 2024 AP Calculus exam packet over here, and we'll be going through each of the problems on our notebook as we have always been doing. And again, we'll go through all 6. Actually, I can write this down right now. So with the 6 free response questions, we'll be going through them one at a time as we take a look here. And so with that, this entire packet will be worth out of 54 points total. So we'll see what our total looks like as well. Last week we did hit a perfect score, which was quite nice. But as always, we'll be going through all 6 of the problems on our notebook, all copied down so we can go through each step individually. And as all of the forms of this test will go, is that we have our trusty TI-83 plus graphing calculator to use on the first 2 problems as we move through this exam. Okay. So, as always, you can submit any of your questions through labcodemath@gmail.com over on that bottom left side, or you can send anything through the live chat so that we can respond to any sort of questions. Hopefully, I'm sure there's going to be a lot of people that are looking for extra study material, so this is hopefully one way to do that. Okay. So, without any further waiting here, we can get beginning on problem number 1, which has a table in T of minutes, and then we have C of T, which is going to be in degrees Celsius on this table, and we will go and input everything in here. So it's 0, 3, 7, and 12 right there. The degrees will be 100, 85, 69, and 55. Okay, so the problem has a bit of context here telling us that the temperature of coffee in a cup at time t, minutes, is modeled by the decreasing function C of t. Okay. So we have that table right there with all of the data points set up right there. So with that, we should be good to begin on problem A here. A little blurry on my side. Our camera needs to be able to focus on that a little bit better if possible. But let's get to problem A first. That's going to tell us to approximate the C prime of 5 using the average rate of change of the function C over the interval going from 3 to 7 for t. Okay, and then we need to show units as well. All right, so average rate of change is a good way to approximate that. I guess they were changing the wording over these years on this exam paper. They actually wouldn't tell you that it's going to be average rate of change, but it doesn't matter. In any case, though, we have the 2 time periods from 3 to 7 in which we will be using average rate of change to determine the first derivative. So by doing that, we will set everything up with the C of 7 on the function subtracted by the C of 3 all over the 7 minus 3. Again, this right here is average unit change set up properly there. So we just need to plug in from the table the values of C of 7 and C of 3. So that will be 69 minus 85 on the numerator. The denominator ends up as 4. Then by doing that, this is going to give us a negative 16 if we do the math properly. So it's negative 16 over 4, giving us negative 4. Now, units-wise, though, remember that the function of C is going to be in degrees Celsius, while it's minutes down at the bottom for T in terms of time. So the units will be degrees Celsius per minute as a rate at which this coffee is cooling. The negative does make sense for us because the temperature is decreasing as the coffee is cooling down over time. Okay. Then moving forth on part B, they're telling us to use a Riemann sum with 3 subintervals. Indicated on the table, let's say to approximate the value of, now we have a definite integral which we're looking at, which is going from 0 to 12 for C of t dt. Okay, and then they're going to ask us to then on the second part of this to interpret the meaning of the 1 over 12 definite multiplied by the definite integral that we just solved for. Okay, in the context of the problem. So with this, we have, again, a few steps to look at here, which, again, first is going to be that Riemann sum approximation of that definite integral using 3 subintervals. And then we need to be able to understand what that 1 over 12 coefficient in front of that integral would mean in terms of the problem. So with 3 subintervals on this Riemann sum, again, this is going to be, this is the left. I forgot to note that down. It's a left Riemann sum. That's what it says on the problem. Which means that we're going to do rectangles, but on the left-hand side. So those 3 heights will be the heights of the rectangles for this, right? So again, by doing this, we are then interpreting this definite integral as, again, this is going to be area of rectangles, right? In this case, rectangles are going to be, of course, a simple base multiplied by a height, and we have to add up 3 of them to get that area that we are approximating. Okay. Remember that the heights are going to be the left-hand heights, and the bases are going to be just the difference between those 2 times, giving us 3 rectangles across the whole time period from 0 to 12. So with that, we can write this out as each of the bases. So first one is going to be 3 minus 0, that difference between the t values along that. So 3 minus 0, then multiply by the left-hand height of 100. Then adding that next with the second rectangle of 7 minus 3 as the base. The height then will be 85 with the left-hand height. And lastly, the last base of 12 minus 7, and then the height of 69 for the left-hand height on that table. So by doing that, we can then put this through with getting us 300 plus the 4 times 85. Well, what am I doing? This is a calculator section. Let me do this by hand. That's question number 1. That's a calculator section. So on the calculator, we can simply put all this through. That's 3 times 100 for the first rectangle. The second rectangle is going to give us a base of 4, height of 85, and our third rectangle is a base of 5 and a height of 69. So with that, that gives us a total of 985 in the calculator. All right, so this is going to be the Riemann sum itself, but then they want us to interpret what that 1 over 12 coefficient would mean for this problem. Right? So something to note is that when we set it up as 1 over 12, then multiplied by the limits going from 0 to 12, what this means is that they're asking for the average value, right, of that function. But in terms of the whole problem itself, if you're looking for average value of C, C being the temperature of the coffee at any given time, of course, this means that this is going to be the average temperature. This average of the coffee from, now of course the limits now will go from 0 to 12, right? From 0 to 12 minutes. right? That is very important because those limits will then tell us from where are we evaluating that average temperature across that time frame from 0 to 12 minutes. Okay, very good. Then going on to part C here, it's going to tell us that we have this new interval for 12 going to t to 20. It tells us that the rate of change of the temperature of the coffee is modeled by C prime of t being equal to negative 24.55 e raised to the 0.01 times t, all divided by t. Okay, so you have that new equation there set out for us. Then they're going to tell us where C prime of t is measured in degrees Celsius per minute, so then that's going to be another rate. But then they want us to find the temperature at time t is equal to 20 minutes. Okay, so they want us to find a specific time from this. Okay, so something to note again is that we have this new interval now. It's not going to be entirely contained in the table, but it does contain one part at least at the t equals 12 mark. So again, at the finishing at 12, it does match from the table ending that what we started with 12 comma 55, right? So we do have the initial condition of C of 12 being equal to 55 degrees Celsius. That's going to be something important to note because that's a starting position for this function, because with C prime of t being here and we want to find the specific temperature, so not the rate but the actual temperature, right? They want us to find C of 20 now, and we need to do all the work to get to that very specific point, right? So how can we do that? We only have the first derivative, but we need to return back to the original function of C. Well, of course, this is going to be a very classic example of using fundamental theorem of calculus and our understanding on how to revert back to an actual original function from the first derivative. So with that, fundamental theorem will have us take the definite integral from, in our case, going from 12 to 20, as that is the time frame that we're dealing with on the problem. If we took that as C prime of t, that is going to be then the difference between C of 20 minus C of 10, right? Fundamental theorem will show that. Let's rewrite that because that is a little bit cut off there. So again, from this, it's the difference of C of 20 minus C of 12, as shown from fundamental theorem by removing back the integral by getting rid of that derivative for one time and then doing the difference of the limits right there. Okay, so because if we want to isolate C of 20, that's going to be instead C of 12, the point that we do know, being added to that definite integral from 12 to 20 of C prime of t dt. Okay, now this gets inputted right into our calculator. C of 12, of course, was already 55, in which we've noted at the start of the problem. Then we will tell our calculator to run a definite integral from 12 to 20 for that negative 24.55 e raised to the 0.01 times t all over t dt. So with that, C of 20 is then going to be equal to that number, in which we'll find out just right there. So this is the line of work that's very important, showing that by moving that point of C of 12 and then adding it to the definite integral going from 12 to 20, that is going to give us the specific point of C of 20 using fundamental theorem as our source right there. So with this, we can do that 55 up front of C of 12. Then we're going to add that with the definite integral. The function integral is the definite integral operation on this calculator. Then we will input in the entire function. So it's negative 24.55 times e raised to the, that's 10. How about e raised to the, there you go, 0.01 times the variable of t. We can put that in right there. So 0.01 times the variable of t. Then we have all of that divided by the variable of t again. Then from there, we'll tell the calculator we're doing this for the variable of t on that integral, going from the limits from 12 all the way to 20 on that variable. Okay, very simple setup for a definite integral of this material. So it's 40.329, 3 decimal points we find, so 40.329 is going to be the result. 40.329 degrees Celsius. Again, that's the temperature at the specific time. That does make sense. We should be cooling down from 55 a bit further as the coffee continues to remain out there in the open. Okay, let's go finish this with part D. So, this is from part C. It can be shown that we have now the C double prime of t, the second derivative of 0.2455 e raised to the 0.01 times t multiplied by 100 minus t all over t squared for the interval going from 12 to 20 on t. Okay, then they're going to ask us determine, let's see from here, determine whether the temperature of the coffee is changing at a decreasing rate or at an increasing rate. Okay. So, because we're going to go over the entire interval from 12 to 20, right? Again, we're going to say, are we changing at a decreasing or an increasing rate? Right? They're looking for the change of the rate again. That's the whole purpose of second derivative. Because if the first derivative, from what we started with, is the rate of change on the temperature, the second derivative will be the rate of change on that change again. We're layering one after the other as a result of the second derivative. So for what we're going to do is that we're going to take a look at the graph of C double prime of t from that 12 to 20 rate so that we can have an idea, because if we're going to be above the x-axis, we're going to be increasing. If we're below the x-axis, we'll be decreasing over that time frame. So we can set up our graphing calculator to show how we're going to graph that. We'll put everything in there. So it's the 0.2455 times e raised to the 0.01 times the variable. Now I have to switch to x because we're graphing on the xy plane. Then that is going to be multiplied by all of 100 minus the variable of x, then divided by the entirety of x to the second power. Okay, so this is the second derivative. Let's go ahead and set up our window so we can show that we're going from, let's see, 11 to 21 should be good because we're only going from 12 to 20, so we make sure that's all contained in there. The y mins and max and negative and positive should be fine. We're only looking for the crossing of the axis there, right? So as we go, it looks like we're going down, but we never actually go underneath the axis. So we're all above the x-axis during the entirety from 12 to 20. So we can draw our conclusion because we never go under, right? So for the interval, the 12 to t to 20, right? C double prime of t is greater than 0, meaning the rate of change of the temperature is increasing. Right? Again, we're taking a look at the rate. The rate is increasing thanks to the second derivative being all above the x-axis for the entirety from 12 to 20 as shown on our calculators. Again, this entire range, all being the graph of the second derivative, is above the x-axis, meaning that the rate of change is then increasing as a result. Okay, that's pretty good. So as what we do over here is that we will be grading these problems 2 at a time. So we'll be moving on to question number 2 before we go back to the answers. As a quick reminder, hopefully, as for those who might be enjoying what I am doing here, make sure to slap that like button on the live stream so that we can continue to do these types of helpful work and problems on the future. So if my camera can easily focus, there's plenty of light here. Hello, can we get this guy to, there we go. Okay, very good. Let's move on to question number 2 before we go back to any sort of grading yet. So question number 2, it tells us that a particle moves from there along the x-axis. So that its velocity at time that t is greater than or equal to 0 is given by the function v of t being equal to the natural log of t squared minus 4t plus 5, all then subtracted by 0.2 times t. Okay, so we have that function set up right there. Then at part A for this problem, it's going to tell us that there is one time that t is equal to t of r in the interval 0 to t to 2 when the particle is at rest. Okay, then we want to find that t of r. Right. Okay, so then secondly they're going to continue that for the interval going from 0 to t to t of r. Now they're asking, is the particle moving to the right or to the left? Okay, and we need to give our reason as such. Okay, so with that, we need to find the time at which this is going to be at rest, meaning that if we plug in that t of r into the velocity, it must be equal to 0. That's of course what it means to be at rest. We can easily do this by the graph, looking at it, because we have our specific time going from 0 to 2, right? So graphing when time is going between 0 to 2, and we can get an idea based off of that first. Okay. So let's set up on our calculator again for this graph here, which is going to be the natural log. Remember, we have to go back to using x because we're using graphing on the xy plane on this calculator. So it's s squared minus 4 times x plus 5, all that subtracted by 0.2 times x again outside. Our window needs to be reset because we need to include all the values that are important here. So going from -1 to +3 to contain the entirety of 0 to 2. And again, positive of -1 should be fine because on the y's, because we just need to see if it crosses that axis so that we can know that it's at rest. So looks like we got 1 right there in between points 1 and 2. So let's go ahead and calculate that 0. So we need to go to the left side of that curve right there, and then go downwards to the right side of that curve, and moving through there, we get the 0 calculated at 1.426 if we round properly. So 1.426. So this is going to be at the t of r being 1.426. Okay. Good. So that's what we have so far as the first time in which the particle enters rest in between that time. Then they're asking, are we moving to the right or to the left beforehand, right? So to look back on the graph, again, before we entered that state of rest, all leading up to that, we're above the x-axis, meaning that the velocity is all positive. Also, in that case, means that the particle is moving to the left, right? So for the velocity of the t, again, in the time in between we reach the time of rest, again, it's going to be greater than 0 within that, right? So the particle is moving to the right before t of r is reached. Okay, so we have our time of rest already set up there from the graph, and our observation that we are moving to the right leading up to that time as well. Okay, very good. So moving onwards to part B here, they're going to tell us to find the acceleration of the particle at the time is equal to 1.5. Okay, then they want us to show the setup for the calculation. Then they want to ask, is the speed of the particle increasing or decreasing at the time is equal to 1.5. Okay, and obviously we need to show all of our work for that. Okay, acceleration now, of course, is then going to be the relationship that the acceleration is known as the velocity, but if we took the first derivative of that, then it becomes acceleration with respect to time. Right? That's what we first need to know. Then if we want to look at speed though, right? So again, our two options that we've gone over many times, and speed up versus slow down. Right? Speed up means that the velocity and acceleration are both greater than 0 or both less than 0, right? So they both need to be positive or both negative to result in a speed up, while the slow down is the velocity is greater than 0 and acceleration is less than 0. Or again, the other way around too, is the accelerate or the velocity, starting with that, is less than 0 and the acceleration is then greater than 0. So if they're same sign, it's going to be speeding up. Different signs means that it is slowing down. A simple result of all of that. Okay, so because of that, they're asking if that speed is going at the time of 1.5. Okay, so first what we can do is that because we have the velocity, again, we can take the end derivative, and this be on the calculator of v of t, specifically at 1.5. That's how we can take a derivative of a function at the specific point that they mentioned of 1.5 right there. And because of that, we can then find that derivative specifically with our calculator right here. So this is the math 8 button for me. So the end derivative is the derivative of a function at a very specific point. So with that, that's going to be the natural log of the, we can go back to using t. So it's t to the second power minus, it's t to the second power minus 4 times t to the, this by itself, and then plus 5 at the end there. And closing that off, we subtract it then by 0.2 times t. Okay. So that's going to be the velocity function. It will tell the calculator this is for the variable of t at the specific point of 1.5. Okay. So we have that all set up there. So we have the derivative at the specific point rounded, giving us -1. So -1, right? There's no units on this. No, there isn't. So -1 is going to be the acceleration at 1.5. Okay, then are we looking at a speed up, slow down? Is that then we need to look at the velocity of 1.5 and plug that in to take a look at the signs. Remember, speed up, slow down is an analysis at the both the acceleration and velocity at a given time. So with that, we will just go and plug everything right in there. So it's natural log of 1.5, all of that squared, then subtracted by 4 times 1.5, and then plus 5 at the end. Closing that off, we subtract it by 0.2 times 1.5. Okay, so this is going to be the collection of the velocity at that specific time of 1.5, giving us negative 0.077, right? So the velocity and acceleration are both negative, right? So we're noting that both the velocity 1.5 and acceleration of 1.5 are less than 0. So it's a speed up at the time of 1.5. So we have our work here and our justification all set up right there. So that will conclude it for part B for this question. Okay, moving on to part C. It tells us that the position of the particle at t is the function x of t at that point, and its position at t is equal to 1 is the function x of 1 being equal to -3. Okay, then they can tell us to find the position of the particle at the t is equal to 4 time. Okay, and we need to show all of that work, of course, as always. Okay, so because we have the position noting as that, remember the relationship here is that if we took the derivative of the position function, that will give us velocity. Right? So taking derivative with respect to time of position will then give us velocity. And because we do know velocity, we need to revert this back into position. By doing that, we once more have to refer to our good old friend, the fundamental theorem of calculus, so that we can set up as a definite integral once more. Again, this time we have the 2 points, right? Because we want to know the position at 4. We only know the position at 1. That means our limits will go from 1 to 4 for the velocity function, meaning that, thanks to fundamental theorem of calculus, we're going to look at the difference of the velocity at 4 and, not velocity, the position at 4 and the position at 1. A simple use of fundamental theorem to revert back from velocity down into position once more, and with a little bit of movement of the this equation, we will get to isolate the position at 4, which is what we're looking for, as the position at 1 added to the definite integral of 1 to 4 v of t dt. Okay, so this will then all be right there. This is our line that we need to follow. So we're going to plug this all in. We already know the position at 1, as they noted on the problem, as -3. Adding that with the definite integral from 1 to 4, the velocity function we plugged right in there from the beginning of our problem as a natural log of t squared minus 4t plus 5, and then subtract that with 0.2t dt waiting out there. Okay, so with just a little bit of movement, the position at 4, with this line going straight into our calculators, will give us the answer that we are looking for. And so we get -3 plus the definite integral of the natural log, all shown right there, so the bottom line right there. So natural log of, we have the variable of t raised to the second power minus 4 times t, minus 4 times t, yep, plus 5, letting that off for the natural log, and then minus 0.2 times t. Okay, this is for the variable of t. Now, of course, our limits here will be going from 1 to 4, and all that is the way that we're going to put this into our calculator. Running that through will then give us the entirety of this answer as -2.83 if we round that properly. So -2.83. 803, sorry, 803. Put that properly, right? So with -2.803, again, negative is fine because this is just the position in reference to the 0. If we're left of that 0 mark, we're going to be negative there. Okay, so all of that goes through just fine, and that should be how we finish off part C. Okay, all right. Yeah, so that will do it for that. So let's go down to part D to finish off this problem before we start grading ourselves here. So at part D, they want us to find the total distance traveled by the particle over the interval going from 1 to t, this time up to 4. So it's already been up to 4. Okay. All right. So this is going to give us our hint right here that total distance, of course, is not going to be just the normal definite integral for that problem. Is the total distance is going to be then, right? So total distance, making sure we understand and remember all of our definitions here, is that it's going to be the definite integral from 1 to 4, like before, but it's going to be the absolute value of the velocity. Oh, sorry, excuse me. It's going to be the absolute value of the velocity function going from 1 to 4. Okay, absolute value, of course, is going to be important because total distance does not care for the sign of the velocity at any given time as we add it up. It's going to switch it all to positive, then add them all up to give us the absolute total amount. So again, no negatives in this calculation going all the way through. Okay, so with this, we can actually just go back to our previous result of our integral as we did, but we're going to get rid of that -3. That's not needed. And then we can easily insert right in to the absolute value. Again, the ABS for me on this calculator. So absolute value of all of that. Then make sure we just close off that parentheses where we need to right there. Not there. One more down right there. There we go. Okay. So again, we're telling it that we're going to take the integral of the velocity function in its absolute value for the same limits of t going from 1 to 4. Okay. So this here is how we're going to do this. It's going to take a little bit of time. The calculator usually likes to crunch out a few extra steps because this all needs to be flipped across the x-axis to make sure all the points are going to be positive. So let this guy run a little bit. Again, a little bit amazing how such a calculator runs only on AAAs, but 0.958 is going to be the amount that the particle travels altogether. Okay, let me make sure that is all set up there properly. Yeah. Because we started -3, yeah, I think we should be fine right there. Yep. So we end up with the total amount of 0.958 as the total distance traveled for the particle that we've had here so far. Okay, very good. So that will conclude it for question number 2. Okay, so we can return back to question number 1 and we can begin our grading. Just as a friendly reminder, hopefully this is being our last exam packet together for this year of 2025. Hopefully our viewers can hit that like button so that we can continue forth doing this kind of work in the future. But nonetheless, though, let's go ahead and get back to our answer key here so we can take a look as we move through this, right? So I have the 2024 answer key ahead of me, and we will begin correcting each point on this. Let me just make sure we swap over to a right highlighter here as we move across this. Yep, so that's a good highlight for us that we can move through. Okay, so going back to question number 1, this is dealing with that a coffee cup that was being cooled. They give us that table right there of the times over the actual temperature. So with that, part A was that we were looking to approximate the first derivative c prime of 5, right, using average rate of change. The setup is exactly the way we need it to with the 2 points, so c of 7 minus c of 3 all over 7 minus 3. And this is how we can go and approximate for a first derivative with the average rate of change. By running through the exact numbers, we get -4 degrees Celsius per minute. Our units do match up. That all lines up. So the actual work, again, of that setup to that average rate of change, as well as the answer itself of -4, will give us 2 out of 2 correct with the units of degrees Celsius per minute matching up exactly what they wanted to see. Okay. Then moving on to part B here, they wanted us to use a left Riemann sum with the 3 subintervals to approximate that definite integral. But then we also still need to interpret the 1 over 12 value as well, right? So this guy on our notebook, again, that has to be interpreted properly as after we do the integration, right? So the setup, of course, is that left Riemann sum means that we take the base, so 3 minus 0 is exactly the way that we set up the first base of the rectangle, multiplied by c of 0, which was 100, as you can see in the line of work right there, right? So we set everything up just right, so 3 times 100, 4 times 85, 5 times 69, all shown there as the right way of forming up a left Riemann sum from the table that we had earlier, then giving us a total of 985. That is exactly what we need to see right there. Okay, so again, the form of the integration and then the answer. Lastly, of course, the interpretation of 1 over 12 for that same definite integral was indeed the average temperature of the coffee. Again, we were taking the average value of C of T, C being the temperature of the coffee at any given time. So by taking that average value, gives us the average temperature all the way from 0 to 12 minutes. Right, so that is a correct interpretation of that as well. So this will give us the full 3 out of 3 correct for part B. All right, very good. Then let's move downwards to part C over here. As we go next, that part C, then we have the rate of the temperature, so C prime, that's the rate of cooling. Again, all listed are right there in degrees Celsius per minute as that unit. But we need to find the exact temperature at T is equal to 20. Right? So going from a rate, we need to go back into a specific time to get a specific temperature, but they do still, from our table earlier, is that we made the note that C of 12, right, the temperature at the very beginning of this function, was given to us at 55 degrees, which is exactly what we need to use fundamental theorem to then set up the way that they were talking about here, which is the C of 20 isolated as C of 12 as the point added to that definite integral, using fundamental theorem for us to set that up exactly the way that they were looking for. Then by running that through our calculator, by plugging in for the function into the integral itself, this is going to give us the C of 20 as 40.329, and cutting off there for rounding is just fine. So again, all this adds up with the setup of the integral, the actual initial condition, making sure we add C of 12 to it. Again, that's absolutely necessary for us to finalize the fundamental theorem of calculus. And then putting it through and getting the answer of 40.329 will give us all 3 out of 3 correct for part C. Okay. Lastly, on part D here, they're asking to see that if we are going to be changing the rate at an increasing or decreasing rate for the rate of change. So by using second derivative and putting it onto the graph, right, we understand that it's going to be greater than 0 for the entire interval that was shown earlier when we did the graph of C double prime of t. So over the entire interval, the second derivative is greater than 0, meaning that indeed the rate of change is increasing for the temperature, right? And it says of themselves right here, the rate of change of the temperature is increasing on that interval, right? And that was a correct way for us to then evaluate for the second derivative using a graph to then show that the rate of change on the coffee, right, that is increasing over that interval. Okay, very good. So that all adds up the way it should. So that should give us everything for part 1 of this exam. So question number 1 is going to be 9 out of 9 correct, as you record our results all the way through. You got all the points possible on that part. So let's go ahead and move down to part 2 before we move forward to finish our corrections here. Is that it tells us that the particle moves along the x-axis for that velocity function. So going to part A, they want us to find that first time of rest where the velocity is going to be equal to 0 at a given time. We had to go do that on the graph. And they also still ask that if it's moving to the right or to the left leading up to that time of rest as well. Okay, so with the time of rest on the graph being 1.426, again, by rounding it, we should be fine. That's exactly the time in which they were looking for. So that checks out for us, 1.426. Okay, but then they want to know that during, leading up to that point, it is greater than 0. Right? We showed that on our graph. That is, as it approached 0, it was from the positive down to the negative. So all positives means that it was moving to the right because the values of the velocity were above the x-axis, reaching up to that point of rest. So all of that adds up properly, giving us 2 out of 2 correct for part A. All right. Then moving down to part B, they want us to find the acceleration of the particle at t is equal to 1.5. Acceleration, of course, was going to be the derivative of the velocity. That's the exact relationship that we pointed out. Then by plugging that in, we get a -1 as a result for the acceleration. That's exactly what they want to see. Again, that was an easy plug into the calculator if you know how to put in for derivatives there. But then they wanted to see is that if the speed of that particle is increasing or decreasing at that specific time. Okay. The way, of course, that we noted is that if they had the same sign in which the velocity also was negative at that time of 1.5 for us, so by both velocity and acceleration having a negative sign, that was enough to conclude that the speed is increasing at the time of 1.5. Okay. So both our acceleration calculation and our analysis that the particle is speeding up because both acceleration and velocity have the same negative sign gives us 2 out of 2 correct for part B. Okay. Going down to part C here is that the position of the particle of time t is x of t, so we have a position graph now, and they give us the point of x of 1 being -3. We then want to find the position at time is equal to 4. Okay. So once more, this is similar to what we did on part A, where we had to do the fundamental theorem. By integrating the velocity, fundamental theorem will allow us to revert back to the positions with the limits of 4 minus the position of 1. So by moving it across, we can isolate the position of 4 as x of 1 plus the definite integral from 1 to 4 of the velocity, exactly the setup that they wanted to see with that, and the initial condition of x of 1. So both the integral and the initial condition of x of 1 were both needed to then get the position at 4, with plugging that in gives negative 2.803. That's the proper way to round it after the third decimal place. So again, all three of those points that they were looking for will give us 3 out of 3 correct for this problem. Very simple use of fundamental theorem. The work needs to show properly and our answer will line up as needed. Okay. Lastly, they want, in part D, they want to find the total distance traveled from 1 to 4. And the setup, of course, is a very simple absolute value of that definite integral of v of t dt. Again, that's how you get total distance, by taking the absolute value of velocity and then integrating. So with that, we get the 0.958, and rounding it to third decimal place, that does match up exactly. Both the setup and the answer are correct, giving us 2 out of 2 correct for part D. Very nice. We're starting off pretty strong with both questions 1 and 2 all giving us 9 out of 9 correct for both of them. Hopefully we can keep that momentum up as we move on down to questions number 3, 4, and then lastly finishing 5 and 6. So something to note, of course, is that the rest of this exam will not be using a graphing calculator. This will be put away as we go down to the last 4 problems of this exam, going 2 at a time. Okay. So let's make sure we revert back properly to our question number 3 as we move forward on this exam. Okay. Looks like question number 3, we might have to do one on the packet, but we'll get to that in just a second here. So we have our notebook here. So question number 3, we'll write this down first, that the depth of seawater at a location can be modeled by the function h that satisfies the differential equation dh over dt being equal to 1 over 2 h minus 1 in the parentheses times the cosine of t over 2. Okay, telling us where h of t is measured in feet and t is measured in hours after noon, which is going to be t is equal to 0. Okay, then lastly they tell us that it is known that h of 0 is equal to 4. So we have an initial point as well. Okay, so all of that is going to be for question number 3 here. Okay, then A is telling us that, okay, A in this case is going to be on the packet, and we'll get to that in just right in here. So the reason why A is going to be on the packet itself is that they give us a slope field to work with on question A for this part right here. All right, this unfortunately I won't be graphing, putting or copying down onto the packet on my notebook, that is, because it's going to take way too long. But we can do it directly on here, and we'll come back to this for us to grade. So that a portion of the slope field for the differential equation is provided, we want to sketch a solution curve, y of h of t, through the point 0, 4, in which they very easily and very graciously put through right there. Okay, so this is another slope field question. Of course, slope fields which are not very often talked about on the exam, but it's something in which you just simply have to, again, if there's any points that we need to follow, you start off with that, then follow along with these slopes as we move across this. It's not a very rigid way of earning points, but it's still something good enough in which if you just follow along the slopes as asked, you'll be doing just fine. So with this, again, idea is that we're increasing, and we see we have a 0 slope around there, and then we decrease afterwards. So we just follow those guidelines of the slope, and we should be just fine. So going through, we're increasing, we hit the 0 slope at that point, and then we decrease downwards like this. Okay, like it doesn't have to be completely 100% exactly what they're looking for, but with slope fields you do get a lot of leeway, at least showing how you follow the increase followed by the decrease, thanks to the tick marks all laid out for us right there on part A. Okay, very good. So that all is really what part A started with. Usually that's 1 point's worth for us. Then we can move on to part B, telling us that for the interval going from 0 to t to 5, it can be shown that h of t is greater than 1. Then from that, find the value of t for the interval 0 to t to 5, at which h has a critical point. Okay. From there, determine whether the critical point corresponds to a relative minimum, a relative maximum, or neither. Yeah, at that point. Okay. So with that, we have all this for part B. Okay. So again, we were looking for a critical point on that, on the interval from 0 to 5. Okay. Critical point, of course, is going to mean that we are looking to see that the derivative dh over dt is going to be equal to 0, right? And right, the number line wise, if we hit that point on the number line, we need to change from positive to negative, or the negative to positive. We need to look for that change in sign at that point where the derivative is equal to 0, so that we can then conclude that it is a critical point, either a maximum or a minimum in that result there. Okay, so with this, right, because we're going from 0 to 5 on that first derivative right there, we can take a look knowing that dh over dt is equal to 1/2 h minus 1 times the cosine of t over 2. Okay, so because we're looking to see that this is going to be set equal to 0, okay, and we know that h of t is greater than 1, so because h is always greater than 1, right, this will never go to 0, right? So again, we know that h is greater than 1 during that entire time. The only thing that could make this entire first derivative be equal to 0, because the h is always greater than 1, it must rely on the cosine of t over 2, right? So the cosine of t over 2, if we want that equal to 0, we need to call back to our good old unit circle as our means to then decipher for something like this, which of course we know that cosine of pi over 2 is then equal to 0, right? And because t can only go from 0 to 5, right, the 3 pi over 2 wouldn't work, because 3 pi over 2 is going to be, 3 pi, at least on the numerator part, is going to be greater than 5. Yeah. So with that, we only have one point of pi over 2, which that's going to be the case, which in case t must be equal to pi for dh over dt then to be equal to 0. Okay? That doesn't necessarily mean that it's immediately a relative minimum or max, because then we need to then look at the number line as pi is going to be equal, pi is equal to t, right, for the function of t. Then we need to look between and after, before and after that remark, so that we can then decipher whether it's a minimum or maximum based off of that. Okay, so at pi, the idea again is that we have the equation 1/2 h minus 1 cosine of t over 2. Remember that all of this, because h was greater than 1, this is always going to be greater than 0, right, for all of that. And again, remembering that h is greater than 1, so all that's going to be a positive coefficient. But because we have cosine, again, going before pi, so anything lower than pi for cosine, of course, with that trig function is going to be positive. And everything after pi, immediately after we hit that 0, is then going to be negative for that. Okay? So, now that we've shown that it goes from an increase to a decrease for that first derivative, right? Again, the first derivative positive means increasing, then it's decreasing, right? Because of this, we can conclude that at the t is equal to pi, h of t has a relative maximum. Just a little bit of a test of our terms here. as we can show that mathematically it's a relative maximum, with the first derivative being positive, then going to a negative, mathematically showing it as such. Lastly, we can go to part C for this problem. They want us to use separation of variables to find the result of y being equal to h of t. Okay, and then we have the with initial condition h of 0 being equal to 4. Okay, so we have that point. We need to now revert back to the original h function on this, which of course we are going to start first with dh over dt being equal to 1/2 times h minus 1 times the cosine of t over 2. Okay, now remember what they told us themselves to do separation of variables, meaning that for us to then revert back to from a derivative to the original function, we need to go take an integral, which means everything including the h's needs to go back to the left side, the dt needs to then go to the right side where all the t's are going to be. So with a little bit of work, we have dh over h minus 1 is equal to 1/2 times the cosine of t over 2 times dt. Okay? So that is going to be the line of work that is needed, so that because all the h's are on one side, all the t's are on the other, we can then integrate indefinitely for both sides of the equation. So this just takes a little bit of work to must integrate properly, giving us the natural log of h minus 1. And we're fine. We know that h is always greater than 1, thanks to what the problem told us earlier. Okay, as well as the fact that we get equal to the 1/2 cosine. So the integrating cosine, of course, is going to give us back positive sign. We can leave it as t over 2 with that 1/2 coefficient matching exactly the way they should be, with that 1/2 in front of the cosine, leaving us with only a plus c as a result of the integration. That plus c is extremely important. You will lose points if that is not there. So for this, we can take the moment here to then solve for c. And we can use that initial point, h of 0 being equal to 4. So h being 4 and t being equal to 0, we can plug that all in. That's a natural log of 4 minus 1 is equal to the sine of 0 over 2 plus c waiting on the outside. Okay. With sine of 0 waiting for us right there, that will give us 0 as a result. Then that means by itself, c is equal to the natural log of 3. Very good. We solve for that constant of integration, and now we just move everything back to get us h as a function of t by itself. So let's revert back. This natural log of h minus 1 being equal to the sine of t over 2 plus the natural log of 3. Okay. So with this, we need to get this h out of the natural log because we want h then isolated on its own. So we raise everything on both sides to the power of e. We can then cancel that out, leaving us with h minus 1 being equal to e raised to the sine of t over 2. Then, because we have an addition inside of the exponent spot now, because you raised everything to there, this is then going to be multiplied by e raised to the natural log of 3. Simple exponent rules, right, of addition inside of the exponent spot, meaning that that can cancel out to just a 3 coming down as a coefficient, meaning that by itself, h of t, by adding 1 to the other side, is going to be 3 multiplied by the sine of t over 2 plus 1, waiting for us right there. Okay. That just took a few lines of work with a separation of variables. Very simple, very straightforward, and easy for us to then get all points necessary on this part. Okay, very good. So that worked out pretty okay. So let's move on to question number 4 before we start grading our results so far. So going down here, we have question number 4 set up here. Okay, so question number 4 is going to give us this graph here. So we're going from, looks like -6 all the way to +6. Yeah, okay. So we can take this guy all the way across, and we can bring this guy all the way down. So we go 1, 2, 3, 4, 5, and 6. We go 1, 2, 3, 4, 5, and 6 right there. We go up to 7, it looks like, on the positives. Go down 2, go up 2. Okay. So at the point, the -6 comma 0.5, we have that listed right there. We have a straight line coming all the way down to separate that. Then at 2 comma 0, we have 0 comma 2, and then 4 comma 0, and then 6 comma negative 1, and we go. So looks like we have here, we're going to curl upwards, then we go straight all the way down here. Okay, so again, this is 6 comma negative 1 that they pointed out for us on that graph right there. And so with this, we have this all shaded in for the region of R, which is all of this right there. Okay, so that's what we have here so far for problem number 4. It tells us that this is the graph of F. Okay, so it tells us here that the graph of F has a horizontal tangent line at x is equal to negative 2, okay, and is linear for the interval going from 0 to x all the way to positive 7. Okay, so we have all that R is bounded. They'll tell us that R is bounded by the line x is equal to negative 6, the x-axis, and the y-axis, as shown for that entire shaded region of R. Very good. So let's move on to part A right here. They're telling us that the function g is defined by g of x being equal to 0 to x f of t dt. Okay. Then they're telling us to find values of g of negative 6, g of positive 4, and g of positive 6. Okay, so we have 3 points we need to find. Now, of course, using the definite integral as in part for the graph that we have. Okay, so let's get to it. So starting with g of negative 6, first you'll notice that we're going from 0 to negative 6 of f of t dt. Right? This is not good because we want to go from lower to higher on the limits. That makes our calculations a lot easier, meaning we have to do a little bit of manipulation on those limits, going from negative 6 to 0, flipping it over, and slapping on a negative coefficient. That's a very simple rule for definite integrals right there. Again, because all this is going to be area underneath the curve, because that's all we have is just the graph, we are taking a negative area from negative 6 all the way to 0. Okay, so with that, okay, also, yeah, let's region R. Region R has an area of 12. I forgot to put that one down. Okay, so let's make sure that is all there. So with this, that's a negative. Again, this is all the region of R, going from negative 6 all the way to 0, as shown on the graph. So with that, we have a negative 12 as a result of g of negative 6. Okay, so that's our first set right there. Then going onwards to g of, our next point is going to be g of 4. That's what they want us to find. So g of 4 is going to give us the definite integral from 0 to 4 of f of t dt. And because this is all the straight line all the way from 4 all the way down, again, 4 is going to be right there. This looks like it's just going to be a simple triangle for us, going from 0 to 4, with that diagonal line coming all the way down. So, of course, it's going to be 1/2. The base then is going to be a base of 4, and the height is going to be positive 2. A simple geometric triangle waiting for us above the axis. So that's going to give us positive 4 as g of 4 as a result. Okay. Lastly, let's go to g of, looks like it's positive 6. So we're going from 0 to 6, f of t dt. Now, because we're going to include the part that already has 0 to 4, and then we have a little bit of extra of that area underneath the x-axis, we can easily split this up from the integral going from 0 to 4 f of t dt, which we found earlier, and then adding that with from 4 to 6 f of t dt. Okay. Simple split of limits here. From 4 to 6 looks like we're going to be underneath, so we have a height of negative 1 as shown on the y value. So from 0 to 4, we have that as positive 4, adding that next with the next triangle. So we have a base of 2, height of negative 1 as you go underneath the axis to finish that one off there. So base of 2, height of negative 1, giving us for minus 1, giving us positive 3 for g of positive 6. Okay, and that's going to be our result right there. Make sure we show that properly. 3 is equal to g of 6. Okay, very good. So that's it for part A. Let's go to part B. They tell us that for the function g in part A, they want to find all values of x in the interval from 0 going to 6, at which the graph of g has a critical point. Okay, and we need to give the reasoning for that. Okay, so if graph of g has a critical point, that of course means that g prime of x must be equal to 0 and must change signs. Okay, so those two must exist for this to result, which of course, if you're going g prime of x, that in this case, because g was already defined as 0 to x f of t dt, right? So again, the idea is that we're taking a definite integral, and then we're taking all this and taking a derivative in respect to x, right? So this is going to use another little bit of fundamental theorem for us to realize we're just going back to the original function f of x. Okay. So because of this, we need to look at where f of x is then going to be equal to 0 on the graph, because that's what f is for us on the graph, and it needs to cross the axis, right? So the graph is crossing the x-axis for us, in which that does happen one time at 4. Okay, and because at 4 it's going to cross from our graph that we see from a positive side to a negative side on the function of f, that must mean that the graph of g is increasing, then going to a decrease, and because of that, right, so g has a critical point if I can spell that, critical point at x is equal to positive 4. Okay, right, which is a local maximum, right? All that adds up with our work, again, us showing that the original function f of x is going to be g prime of x from what we had earlier on part A. Okay, all right, very good. So then let's go over to part C here, that the function h is defined by h of x being equal to, going from -6 to x, f prime of t dt. Okay. Then they want to find the values of h of 6, h prime of 6, and h double prime of 6. Okay. They want us to find all of these for that relationship right there. So starting off, h of 6 is going to be pretty straightforward. If you just plug in 6, that's the integral going from -6 to +6 of f prime of t dt. Of course, us understanding with fundamental theorem of calculus, that is going to mean by integrating a derivative, we're taking a step back to the standard f of 6 minus f of -6. Okay. F of 6, as we show on the graph, is going to be -1. So that's -1 subtracted by f of +6 being positive 0.5. F of -6 giving us positive 0.5 as a result. So -1 minus 0.5 is going to be a -1.5. And that's h of 6. Okay. So that's our first point recognized right there. Then moving forth, we have h prime of 6. Right. So the idea is that we're going to take from -6 to +6 f prime of t dt. But we are going to take a derivative in terms of x one time for this, meaning that we can then replace, we're doing x first, right? So by doing this, again, using fundamental theorem again, by taking a derivative of an integral, that means we just get left with f prime of x as a result. So plugging in that 6, f prime of 6 that we have earlier, right? F prime at 6, and the idea here is that because we are moving on that slope of the line, as you can see, we went across 2 and we went downwards 1 from the point from 4, 0 down to 6, -1. So because of that, we have a slope of -1/2, matching that exactly from the graph. Okay, so again, a rise of -1, a run of 2 gives us -1/2 as a result. Okay, again, this is going to be h prime of 6 from that. And the h double prime of 6 means that we can go and start looking at this one more time. So again, this is the same integral. Okay, but then because we're taking derivative and doing that a second time after the fact, right? Of course, you need to know is that we can go back to doing the f prime of 6, and then we're taking one more derivative in respect to x, giving us f double prime of 6. Okay, which of course double prime would mean that we're looking at concavity, right? So if the first derivative was asking for slope, the second derivative will be concavity at the point of +6 for the graph of f. But because this is a straight line, there is no concavity, right? There's no change in the slope, so that concavity is going to give us 0 because that is a straight line. Okay, so with that all there, that will conclude it for question number 4. And now we can revert back to starting to correct our responses here. Again, just as always, hopefully the people that are still looking at this can hopefully drop a like as we move across this next part of the exam. So with that, we can take a look here. So we can go back to question number 3 first. So we're going back to the question about that seawater with the dH over dt, which of course we did the first part on the packet itself. All right, so that was with question A, which is done on the packet because that dealt with a slope field, is that with that differential equation, we can look at that solution curve that does match about correct. Again, they just want to see that our solution curve is increasing. We have that horizontal tangent line waiting for us up there, and then we decrease afterwards, right? A very simple 1 point. They just want to make sure you're getting somewhere close to this as we follow along the guidelines of the slope field itself. Okay. So with that, that is going to give us 1 out of 1 correct for part A. Okay, then moving downwards to part B here, we have the h of t being greater than 1 for that entire time. Then we want to see if we're dealing with a relative min, max, or neither at that point in which it's going to be equal to 0 for the critical point, right? Okay, so because we have, right, the dh over dt going to go to 0 from our line of work there, right? We did show that cosine of t must be equal to 0, right, as shown with our work, which means that t being equal to pi is going to be the critical point. But then moving that downwards, though, is that because beforehand we're greater than 0, going from 0 to pi, right? And then from afterwards, we're going to be less than 0, right, as shown on number line graph. Again, with cosine, as we approach pi over 2 from the left side, we are positive, then we go negative after the fact. Again, cosine, just a little bit of work to understand how that shows in terms of that graph. So because we were going from a positive on the derivative, then to a negative after the critical point, that shows that it's indeed going to be a relative maximum on that point. So because we set the dh over dt equal to 0, we have t is equal to pi from work, and lastly, our justification that it's a relative maximum because of our number line analysis there. That gives us all 3 out of 3 correct for part B. Very nice. Okay. Very lastly, we're going to go down to part C here, where we want to look at the particular solution of the differential equation with the initial condition, h of 0 being equal to 4. And once more, we're using separation of variables to then move this around so we can set up for the integrals on both sides. Again, they want to show dh over h minus 1 multiplied by the rest of 1/2 times cosine times d of t. All that is exactly what they wanted to see on our line of work there. Then by integrating, we get the natural log of h minus 1, then equal to the sine of t over 2 plus c on the outside. Again, no need for a coefficient. That's already taken care of thanks to chain rule. Then from that, we will then solve for c, getting a natural log of positive 3 for c by plugging in the 4 and the 0 into the equation that we have. Then lastly, to move everything over by looking at how to get rid of h from the natural log spot, putting everything onto one side, we get 1 plus 3 times e raised to the sine of 2. What happened? Oh dear. Okay. Looks like I did a little bit of an oopsie. Because for whatever reason, I did not keep that e raised to sine over 2. So Unfortunately, that looks like we have everything listed properly, except we needed to show that we still have 3 times e raised to the sine of t over 2. That needs to be shown. I don't know where that e went earlier, but the plus on the outside is exactly still correct. So unfortunately, I will be missing out on a point here, but going through one thing at a time here in terms of how they grade it is that the separation of variables did indeed happen the way that it should have. Then by running both both integrals of the natural log h minus 1 sine of t over 2 with that plus c, very important to keep that. Both of those will be correct. Then by solving for c being equal to the natural log of 3 after plugging it back in, that will give me another point, but I will not get the last point of getting the correct h of t because I eliminated the e for whatever reason. Looks like I didn't copy that over correctly. That's a very sad and silly mistake. Everything was working to the way that it should have been, except for the last step. So unfortunately, that oopsie will cost me a point out of 8 out of 9 because I did not keep that e there where it should have been. So with that, that is a great lesson to make sure that we are looking back at our work to make sure we align everything properly. That unfortunately breaks our perfect streak so far, but nonetheless though, it still allows us to focus on getting the best that we can on the rest of the exam. Okay, moving on over to question number 4 here. We're dealing with that graph of f. And so the function g that was defined with that definite integral, we need to look at those 3 points, -6, 4, and +6. So with that, going through, again, we had to make sure we put that negative on that first derivative for g of -6 because we need to swap those limits to being low to high. And because of that, we get a result of -12 on g of -6. That's pretty good. Then going on to 4, again, moving that through, we get +4 there, and then +6 means that we have to add that negative triangle there, giving us +3. All those 3 match up, giving us a total of 3 points on part A. Very nice. Just lots of simple work on areas and fundamental theorem, so pretty simple. Moving on down to part B here, is that because we have the interval from 0 to 6, we want to know where g has a critical point. Because g was already defined as the integral of f, by taking its derivative, we just need to see where the original function f, right, is going to be equal to 0 from our line of work, which shows at 4 that's going to be the case, which indeed is going to be the critical point, right? So fundamental theorem, again, that usage of understanding that by taking derivative of g, we get f. That's exactly what we need to do to then solve for the actual point itself. So that's 2 out of 2 correct for part B. All there. And lastly, to part C on this problem, we have the function h now, which is the definite integral, but of f prime of t, shown right there. So now we have 3 more points to find: 6, h prime of 6, and h double prime of 6. So with that, for each of them, with h of 6, that's a simple usage of the fundamental theorem, giving us f of 6 minus f of -6 as shown, giving us -1.5. So that indeed shows up properly. Okay, then for the h prime, that means that by taking h prime, that means it's f prime of 6, which gives us a slope of -1/2, because that was shown on the line. Again, at +6, we have a slope going from 2 across, 1 down for that straight line all the way through, giving us the exact slope of -1/2, as is what is asked for on a first derivative. Then lastly, for h double prime of 6, that means that we are going to look at, to make sure that we take a second derivative, meaning that we're looking at f double prime of 6, the concavity of a straight line at that point is going to be 0. Okay? So all those add up with the way of us using fundamental theorem, then all 3 points, giving us a total of 4 out of 4 correct on part C. Very nice. So it looks like we've picked our pace back up, although we missed a silly one on question number 3. We're back to getting full marks on question number 4. Okay, very good. So let's move back here and let's go and finish these last few problems here. Hopefully, again, for those that are still watching, that you are enjoying what you see here as we finalize our last live stream together for this exam. Again, the actual AP exam for those in the United States is this Monday, coming up in the morning. So hopefully, for after all that we've studied, that will show up properly. Okay, looks like I stapled my papers a little bit weird. Where is question number 5? What? Oh dear. Okay, well, I think I need to look at question number 5 online because my printer did not print properly on this guy. Okay, cool. Yeah, okay. Well, I'm going to have to go take a look at question number 5 online in the meantime, so that way we can have that all written down correctly. Just a moment here. Going down to 5. Okay, I've copied this down and then we'll just go on through. So, question number 5 is telling us to consider the curve. So this curve is going to be defined by x squared plus 3y plus 2y squared is equal to 48. Okay, and then it tells that it can be shown that dy over dx is equal to negative 2x all divided by 3 plus 4y. Okay, so we have that listed out right there. Okay, then for part A, they're going to ask us that there is a point on the curve, okay, near 2, 4 with x coordinate, okay, of 3. Okay. Use the line tangent to the curve at 2, 4 to approximate the y coordinate of the point. Okay, very good. So to get this started with, right, we have the first derivative and the original curve, but we want to do a line tangent at 2, 4 so we can approximate at the x value of 3. Okay, which of course line tangent means that we need to go and use the point slope form, which was what they like on the exam. Y equals m of all of x minus h plus k. And this is going to be using the point h comma k, which already for us is 2, 4 as a line tangent at that point. But we're, in our case, m is going to be also the dy over dx, so that's slope specifically at 2, 4, right, evaluated for that point directly from our moment right there, giving us the negative 2 with x plugged in for 2, 3 plus 4, and then 4 plugged into 1. Okay, so that is exactly how we get all this set up here. So giving us negative 4 all over 3 plus 16, so it's 19, right? That's going to be the slope. That's the point 2, 4. So with that, that's a very simple arrangement of the line tangent, giving us y is equal to negative 4 over 19, x minus 2 plus 4 waiting for us on the outside. Okay, very simple to do a tangent line equation, but we still need to then approximate for x is equal to 3, right? So in this case, y of 3 for us is going to be negative 4 over 19, 3 minus 2 plus 4, giving us negative 4 over 19 plus 4. It looks like we can convert this into a simple singular fraction here. So the 4 with the over 19, well, that's a little bit of an odd number, but nonetheless though, with the 19 there, it's gonna give us what, 80, so 76. So it's 76 over 19 as the improper fraction. So that's gonna give us negative 72, positive 72 over 19, right? And that is gonna be the y coordinate. Again, that means that the point 3 comma 72 over 19 as the approximation from the line tangent. Okay. That adds up pretty okay. Then moving downwards to part B here is that they're asking, is the horizontal line y is equal to 1 tangent to the curve? Okay, and we need to give the reason for that. Okay, so if we have the horizontal line y is equal to 1 tangent to the curve, right, we need to be able to touch that curve exactly at 1 point. Is that going to be the case, right? If that's tangent, that means that for the original, right, x squared plus 3y plus 2y squared is equal to 48, right? Will we get a singular point in which this is going to be the case, right? So you plug this through x squared plus 3 plus 2 is equal to 48. Giving x squared is equal to, subtracting the 5 gives us 43. So x is equal to plus or minus rad 43 on that first part. Okay, so it looks like there are some x points in which that's going to be the case. But then we also need to take a look to see. Wait, hang on. Sorry, the x doesn't matter actually. So yeah, well, in the case that we do have an x right there. But if the y is equal to is going to be tangent to that, right, that means that, again, this is a horizontal line. Think about this, right? So we have y is equal to 1 as a horizontal line. It needs to touch the curve at exactly 1 point right there as you go down. Which means, again, a horizontal line means that the derivative dy over dx must be equal to 0 at the y is equal to 1 mark. Okay, so let's see if that's ever going to be the case here, right? So let's plug this in. So it's dy over dx, again, at y is equal to 1 is negative 2x over 3 plus 4y. Again, plugging in y is equal to 1, and this should be equal to 0. Okay, so with that, this gives us negative 2x over positive 7. In this case, x just needs to be equal to 0 for that to work. Now, does that work? That's where our work earlier made sense here, because if we plugged in 0 back into the original curve here, we get 0 squared plus 3 plus 2. Again, this is going to be at the point 0, 1, which in this case, with this not being equal to 48, as shown, that is not a true math statement if we plugged in for y is equal to 1 and x is being equal to 0, right? This is going to be, right, this will be not true. So again, the line y is equal to 1 is not tangent to the curve, right? We've shown that the horizontal line with its horizontal slope will never touch the graph at any point, right? Because of the way that that works. Okay, so that works. Then going down to part C here is that they're going to continue that the curve intersects the positive x-axis at the point, the positive rad 48, 0. Okay, and they're asking, is the line tangent to the curve at this point vertical? Okay, so more questions about tangent lines were that if it's a vertical tangent line to the curve, that must mean that the derivative, so dy over dx, if we plugged in for the point radical 48, 0, it must be undefined, right? As is, right, vertical lines, of course, slope-wise means that it's undefined. There is no change in the x, but there is an infinite change in the y, making it undefined on that ratio. So because of that, we can take a look to see what that looks like. So with negative 2 times rad 48, all of 3 plus 4 and then 0 plugged in for the y, we get negative 2 rad 48 all over 3, which is indeed is not undefined. So we will conclude that the line tangent to the point, the rad 48, 0, is not undefined. Okay, so our work, again, very straightforward, but still very needed to show every step to see how this will be resulted from the definitions that we know already. Okay. Lastly, on part D, they tell us that for the time is greater than or equal to 0, a particle is moving along another curve defined by, we have this equation, the y to the third plus 2x times y is equal to 24. Okay, so at the instant, the point is at 4, 2. The y coordinate let's see, other particle's position is decreasing at a rate of 2 units per second. Okay, then the actual question is, at that instant, what is the rate of change of the x coordinate? Okay, so we've got a lot of things going on here. Hopefully I don't know if we can actually shove this all into this last bit of paper here, but let's have a look. We flip over if we need to. So we have another curve here with y cubed plus 2xy is equal to 24. And we have a y coordinate, right? We have it's decreasing at a rate of 2 units per second from this, okay? At the specific point of 4, 2. Which means, again, what they're telling us is that the dy over dt, the change in y in respect to time, is -2. Okay? And of course, they want us to look at it instead dx over dt at that exact point, and they need to look at what that is. Which means we need to do implicit differentiation again, right? Implicit differentiation, meaning that for each of them, right, because we're doing it implicitly, look, as you can see, we have dy's over dt and dx over dt. That means that if we took a derivative of x, that goes to dx over dt, and it took a derivative of y is equal to dy over dt. Right? Okay. They do not go to 1. They go to those results because we're doing it implicitly, as each of them are changing in respect to time. So it looks like I will need to flip this over for us to then do this properly. So we are going to, again, take a derivative of all of that curve. So it's y to the third plus 2xy is equal to 24. Again, all of this needs to be taken its derivative now with respect to time for this. Again, remember, we have to understand we have chain rule coming across for all of this and a few exponents and product rules. But what also is going to be important is that it's this for the 0.4, 2, and we already know that dy over dx is -2, and we are looking for dx over dt. We do not know what that is. Okay. So because of that, let's run this differentiation and let's see what we can get. So with a little bit of chain rule here, that's an exponent rule. That's 3y to the second power. Remember, the derivative of y does not go to 1. It's dy over dt for that first term right there. Then it looks like we have product rule that we need to keep track of with 2 times x times y. So product rule will then dictate that we do take the derivative of x first. So it's 2 times y. Derivative of x goes to dx over dt. Then we're going to add that with the next one, which is going to be the derivative of y multiplied by the rest of that, which is going to be 2 times x times dy over dt. And lastly, 24 is a constant number. It'll just go to 0. Okay? So this is the result of our differentiation. Now, because we are isolating for dx over dt, let's get to doing that. So 2y dx over dt is equal to -2x times dy over dt, then subtracted by 3y squared dy over dt. Right? Moving everything over, then lastly, by itself, dx over dt is going to be equal to -2x dy over dt minus 3y squared dy over dt, then throwing everything underneath as 2y. Okay, so now dx over dt is isolated, exactly what we want to see. Now we just need to plug in for the x, the y, and the dy over dt. What am I doing? dy over dt that we gave as -2 from the problem. So by doing that, we just run everything through. So it's -2, x is +4, dy over dt is another -2, subtracted by 3, y is +2 squared, dy over dt is -2 again, all divided by 2, and y is +2. Okay, so that's a pretty simple line of work. Then putting this all through is that we get, looks like this is a -16 on the first part right there. So -16 subtracted by 3, 4, and -2 all multiplied together. That's -24 with a negative on there as a subtraction. That's +24 waiting for us right there. And then +4 in the denominator. That gives us a +8 over 4, giving us +2 as dx over dt. Okay, so there you have it. That is going to be the result of that work. Again, just a little bit of back and forth on a little bit of implicit differentiation for this problem, but pretty straightforward for what we need to do for us to do that. Again, this is going to be units per second. That's what they want to see for part D. Okay, very good. So with that, we will go to our last problem, problem number 6 on this before we finish up this entire packet. Okay, so question number 6 right here is going to be another graph right here. Looks like we go up 5 spots here, then we go across 5 spots here. Okay, so let's go 1, 2, 3, 4, and 5 right there. 1, 2, 3, 4, and 5. But the y value is increased by 5, so 5, 10, 15, 20, 25. Okay, so that is going to be the graph setup right there. Then we have a vertical line at +2, a vertical line at +5. Okay, then we have the first function going up like this, starting at underneath 5, so it goes like this. This is going to be f of x, shown right there. And then we have another function starting at 0, looks like we go underneath, and then we cross at 2. So we go like this. Okay, and this is g of x right there. Okay, so all of this is the area of R, and then all of this going from here is the area S. Okay, all right. So with this, they're going to tell us that the functions f of x and g of x are defined by, now we have these guys, two equations, so it's f of x is equal to x squared plus 2, and g of x is equal to x squared minus 2x. Okay, so we have that all listed out for us right there. Then going to part A, they're telling us to let R be the region bounded by f g x is equal to 0 and x is equal to 2. Okay, but now from that region that we show already on the graph, they're telling us to write but do not evaluate an integral expression that gives the area of region R. Okay, very good. So we need to look at the area of region R, of course, which in this case area is going to be equal to, again, any sort of definite integral. In this case, it's always the top function minus the bottom. Right? For us, dx works because we're going horizontally across the limits. So because of this, we can set up the area as, now for us, because it's x equals 0 to x equals 2, those two vertical lines at the start, right, going across, that's going to be our limits going from 0 to 2. The top function, as you can see, is be f of x for us, and the bottom function is g of x, right? So in this case, this is going to be f of x minus g of x dx. Okay, this should be fine, at least for part of our answer. If we really need to show it, again, if we want to substitute everything in, that's 0 to 2. F of x is all of x squared plus 2, then subtracted by x squared minus 2x dx. Okay, either of those should be fine, but I think this one is just fine enough as a way to set up, to understand which one is going on top, which one's going on bottom, and a little bit of substitution if you were going to do it by hand. Thankfully for us, we're not going to, so we leave it as that. Okay, then they're telling us that let S be the region bounded by G and the x-axis from x equals 2 to x is equal to 5. Okay, so then they're going to continue that region S is the base of a solid. Okay, then for the solid, at each x, the cross section that is perpendicular to the x-axis is a rectangle. They're telling us that with height equal to half its base in region S. Okay, then they want to find the actual volume of the solid. All right, quite a bit going on right there, right? Because they're telling us that region S, which is this guy as we've shown right here on the graph, right? It's just g of x and the x-axis right there. But if we want to show it a little bit better here, is that if we want to show this, right? So we have that region right there. So that's the y-axis, that's the x-axis. We have rectangles coming up like this that are all going to need to be added up to make up the entire solid in the third dimension, right? So I've gone over that in detail a number of times on the YouTube channel, but nonetheless though, if we are looking for a volume, right, again, this is going to be the integral of the area, right, to then give us a volume, right? Integrating a line gives us an area. Integrating an area will then, of course, give us a volume, okay? So for us though, is that the area in question here are going to be rectangles, right? And they told us already that these rectangles, it says the height is half of the base, right? So with the normally it's base times height for a rectangle. They told us that the height is equal to half of the base. So in this case, it's base times 1/2 times the base again, giving us 1/2 base squared as a result for the area of those rectangles coming across this area. Okay, and because of that, again, the base, of course, is going to be in our case g of x, as was shown on the start of the problem. And because g of x is our function in question here, that means we can set up the volume as the definite integral. And because we're going from 2 to 5, and that's a number 2 right there. So 2 to 5 as our limits, that means it's going to be 1/2. And then the base, which is g of x, is going to be x squared plus 2 x squared. Oh, sorry, it's x squared minus 2x, all that squared. Okay, so first let's take a step back here. So again, this is going to be 2 to 5 of the 1/2 g of x, and g of x is being squared. And because of that, the volume is going to be 2 to 5. To clean that up, it's 1/2 x squared minus 2x, all that squared dx. Okay, so this is how we're going to run this problem right here. If our camera can focus on that, please. So a little bit more, we're almost done here. So because of that, right, we can set up this problem here. First, I would personally like to FOIL this out, leaving the 1/2 coefficient. So that's 2 to 5 of all of x to the 4th minus 4x squared. No, it's not. It's 4x to the 3rd plus 4x squared. Simple algebra foiling right there, and then dx. Keeping track of what we have in the parentheses right there. Okay. Then by running this entire integral, this is going to be 1/2 all of x to the 5th over 5, then subtracted by x to the 4th, that works out fine, and then plus 4/3 x to the 3rd power, going from 2 to 5. Okay. So that's going to be the result of the integral itself. Then let's go ahead and solve for the volume now by running this. So this is going to be all of, in two sides, 5 to the 5th over 5. Now this can work out on itself, 5 to the 5th again. So this is 5 to the 5th over 5, meaning that it's just 5 to the 4th. Just a little simple amounts of work to make our lives easier. 5 to the 4th is going to be 625, which is 25 times 25. 625 minus 5 to the 4th, again, that's another 625. Plus 4/3 x to the 3rd. X to the 125, so 125 times 4, that should be 500. So it's 500 over 3. That's the first part, that first limit of 5. Then we need to subtract it with the second limit of positive 2. 2 to the 5th is 32, so it's 32 over 5 minus a whole 16 plus 4/3 x to the 3rd, which would be 8 times 4, so it's 32 over 3. And that is how we're going to set that one up there. The 625s will cancel quite nicely. Okay. Let's see here. If we can do, it looks like we need to do a common denominator of 15 across the board, it looks like. So 32 over 5 is going to be 96 over 15. 16 and 15. What's that? 16 and 15. That will give us 80 and 160, so 240, right? 240, wait. 80 and 160. Yeah. So 240 over 15, and then 32 times 5 is 160 over 15. Okay. Just a little bit of fractional work right there. The 500 over 3 will then be 2500 over 15. So just making sure we have all the common denominators all worked out for us right there. So with this, let's see, 240, 160, we take off an 80 from the remainder there. So it will be 2500 over 15, then subtracted by, so that's going to be just 16 over 15. Giving us, in total, the amount is going to be 2484 over 15. That is not divisible by 3, is it? 2 and 6? No, 12 and 6. 18. Oh, that should be divisible. Okay, we can simplify that. So we take out a factor of 3, giving us 8, 2, and 8. So by canceling that, that's going to be 828 over 5 as the total volume. That took a little bit of time. Unfortunately, we don't have a calculator allowed in this section. Hopefully that work does match the way that it should. Half of its base. Yeah. Okay. I think that should be fine. We have, oh yeah, anyway, we still have that 1/2 coefficient waiting for us. So let's make sure we keep that in mind. So 828 times a 1/2 is me 414 over 5. That should be the result right there. Okay. Huh. Okay. That was a little bit odd, but I think we should be fine. So let's go lastly to part C here, telling us to write, but do not evaluate. An integral expression. Let's see, that gives the volume of the solid generated when region S is rotated about the line y is equal to 20. That's a horizontal line. Okay. Well, unfortunately, we are out of space. That took up a lot in part B. Well, I don't think it really should have. But nonetheless, though, we are rotating about the y equals 20 horizontal line. So let's have a look here. Actually, no, before we switch it over. So, keep in mind is that with this original graph, if we have the y is equal to 20 horizontal line set up right here, and that's y is equal to 20, we are rotating about this guy, and we need to make sure we keep in mind this rotation for a region of S. As we flip it around, we have all this negative area right there, and then the actual area reaching all the way down. Okay, so something to note, of course, is that if we are doing a rotation, that means we need to go and do the washer method. And so we still need to keep in mind that g of x is equal to the x squared minus 2x. So again, the washer method is going to be the volume being equal to pi on the outside, again, a to b for our limits, I'll call it big R squared minus little r squared. Right? Again, these are going to be the radius in which they are being rotated, because you make circular rotations about an axis of rotation. Okay, so for us, that means we need to understand what big R and we understand what little r is going to be for this guy. Okay, so let's turn back to our previous problem here, the graph, right? Again, think of these as radius as they get rotated about. Okay, as you can see, the larger radius here, right, is going to be reaching from here all the way down to the very bottom axis, and that is not going to change. Right? What is going to change is that the little r will then be following across, right, the g of x function, and we need to take them all out, moving up closer and closer to y equals 20 for the region of S. Okay, so with that, something known as that the big R, again, that means that that was a total radius being completely rotated, which is going to be a flat 20 because that was a distance between the axis and the line of rotation. But little r, though, then is going to be 20, then subtracted by g of x, because we are removing that just to make sure, right? And again, that g of x line right there, right, is being removed from the actual line of 20. And again, we need to cut all that away, right, from the actual amount. Okay, so by subtracting by g of x, we're subtracting less and less as we move across g of x, keeping that region of S left alone as you rotate it down. Okay. So because of this, this means that we can then set this up. Of course, our A's and B's is going to be, right, going from, is it 2 to 5? Yeah, 2 to 5. Right, big R being all of 20 squared subtracted by little r of 20 minus g of x, all that squared dx. And there you have it. That is a pretty easy setup right there. Written nice and clear for all of us as we finally conclude this exam. Okay, so that will do it for that. So let's go back to problem number 5 and let's begin our corrections here. Okay, let's move everything back here so we can begin our corrections. Back at question number 5. Okay, so we have that curve that they talked about. They just gave us that equation and then the differential equation of the first derivative set up right there. So problem number A, they wanted to do the line tangent at the 2, 4 point, so we can do an approximation of 3 on the next point. Okay, so because of that, we then will have to do that first derivative again, evaluated at 2, 4, giving us that slope of -4 over 19. The slope of the tangent line at that specific point of 2, 4 was done quite easily. Then by plugging that into the line, that gives us 72 over 19 exactly as the result. So both the slope and the point as a result will give us 2 out of 2 correct for part A. Moving onwards to part B, they're asking, is the horizontal line y is equal to 1 tangent to the curve? Horizontal line, of course, meaning that the derivative must be equal to 0. That's what we came up as well as a conclusion. Because we're using a horizontal line as a tangent to any sort of curve, that must mean that the first derivative is equal to 0 at that point. But because 0, 1, right, because we plugged that guy in there, right, giving us the result that the x must be equal to 0 for that derivative to be true. All right, 0, 1 did not fit inside of the actual line equation, so therefore that point does not exist for that and is not going to be will not be tangent to the curve, right? So both are consideration that the first derivative must be equal to 0 for a horizontal line to be tangent, and then the result that y is equal to 1 will no longer be tangent after our work will give us the full amount of 2 out of 2 correct for that part. Okay, very nice. Then onwards to part C here is that they're telling us that the curve then intersects the x-axis at rad 48, 0. Then they are going to ask if that line tangent is going to be vertical this time, right? A vertical tangent line, of course, would mean that, right, the denominator, well, they said here the denominator is 0, yeah. The denominator must be equal to 0. For in our case, again, we describe first it must be undefined, which of course means that we need a 0 in the denominator. But of course, it came up to an actual fraction. It is not undefined. Therefore, it will not be vertical at that tangent line. Okay? So again, if you want verticality, that means the denominator must be equal to 0. At the point which they provided to us, the derivative was not equal to, the derivative did not have the denominator equal to 0, meaning that we still get 1 out of 1 correct for our work to show that to be the case. Okay. Then moving downwards to problem D here is that, again, we have that particle moving along a different curve defined as y cubed plus 2xy is equal to 24. And at the point at 4, 2, so they have a specific point again, but they gave us the change of y coordinate at a rate of 2 units per second for the y, but we need to look at the rate of change for x instead, right? Of course, what that means is that we need to then, because they gave us dy over dt is -2, we need to then solve for dx over dt after doing a round of implicit differentiation, right? So we ran out of space here. We actually continued on the back on the next page over. So we ran the first derivative of that curve that we started with, and answer key will give us the result of exactly, we have 3y squared dy over dt plus 2y times dx over dt plus 2x times dy over dt. And that was a lot of chain rule and a bit of product rule for the implicit differentiation that they're looking for. So that matches up exactly what they needed to. Okay, then we must set it equal to 0 because that's the result of the differentiation. Right? Then running it through, we get the actual, remembering that the change in y in respect to time is -2. And by plugging everything right in there, we get the result of dx over dt being equal to, they tell us, +10. Very interesting. Did they swap? Oh dear. Okay, that's where the mistake was. Well, that's unfortunate. Another little oopsie for us. I literally had a negative and another negative there. That should have been a +16, giving us a +40 over 4, giving us dx over dt to be equal to +10. So sadly, again, another sad mistake because there were 2 negatives. I only counted for 1. That gave us the wrong result of dx over dt. So because of that, that is no good. But still, because we have the implicit differentiation and the correct plugin of -2, again, the plugin was correct. The actual result, the answer was not. That would only give us 3 out of 4 correct, sadly, on part or number 5. Okay. So again, everything was working out correctly. Our line of work, our differentiation, just sadly the analysis, or not but the actual last solving of our work did not end up where it should have been. That's a bit unfortunate. Again, everything here was correct. The plugins is just that the negative sign was not carried properly. Nonetheless, though, we will then finish up with question number 6, and we'll see to it that we get our result on our last practice here together. So question number 6 dealt with that graph there with regions R and S with the f of x and g of x listed out for us right there. Okay. So question A, though, they said that we want to look at the area of region R. So specifically the area region R, this region up there, right? So we want only the area, which means that we set up as 0 to 2, right? The actual limits of integration of the top minus bottom function. For us, the top function is f, the bottom function is g as you follow the curves. So both the integrals set up properly, and then, right, the actual result will both give us, right, by setting up f minus g inside of the integral from 0 to 2 will give us 2 out of 2 correct for part A. Okay, very good. Then going downwards to part B here, S is going to be the region that they're looking at. Again, so now for S being the entirety from that point right there, just between g of x and the x-axis only, right, they want to know that if we had cross sections perpendicular x-axis as rectangles instead, we want to find a volume that comes across from those limits instead. Okay, so because we're looking at a volume question, again, it's the rectangles of the area then need to be set up inside of the integral, but the rectangle is special in the sense that the base times 1/2 of the base, right, because the height is 1/2 of the base of that rectangle, we can get that set up inside of the integral. Okay, so by putting the limits together from 2 to 5 and the right setup of 1/2 times x squared minus 2x raised to the second power, because again it's b squared, the base squared, to get us that rectangle. Right, we set that all up, we run the integral all the way through, right, with the result of x to the 5th over 5 minus x to the 4th plus 4/3 x to the 3rd power. Right, so all that is a correct way of doing the actual integration. Then we need to evaluate from 5 over 2. Then by running the actual work, it took us a little bit to simplify a bunch of fractions. That's a little bit of scratch work off to the side. But by putting everything through, we get the result of 414 over 5 as a result of the volume, and that all matches up. Right? This took a little bit of steps for us to understand how to get a volume from an area of a rectangle. Again, they gave us a special relationship of base times 1/2 of the other base, of the same base that is, giving us that area. So going all the way down, right, the correct setup, the correct integral, and then the correct answer will give us all 4 out of 4 correct on part B. Very nice. Okay, and very lastly here, we have part C, where they're telling us to write but not to evaluate the integral expression that gives the volume, where we're going back to region S again, but we're being rotated this time around y is equals 20. Okay, so we're not doing a simple geometrical, and we're doing a rotation across y is equal to 20. So again, as shown here, right, the y equal 20 line is somewhere up there on our graph, and we're going to do a rotation, meaning that we have to remember all of this area to be removed, as well as the shaded region then to be calculated there. Okay? This means that we had to go and employ on our backside here that we are using the washer method here, which is going to be pi on the outside, the limits of that r big R squared minus little r squared, our larger radius, again, is the amount that goes from that the y is equals 20 line, again, all the way down to the, what is this here? I don't know what that. Okay, so this going all the way down to the bottom there, right? Again, that needs to be all removed while we keep all of this, right, the entire radius all the way through. We just need to subtract off g of x from the 20 moving all the way up. Okay? It might be a little bit difficult for some students to really visualize that, but that's kind of what you do need to see, as the larger radius is a flat 20, the smaller radius moving across. Remember that we have the smaller radius, right? Again, think of it like this, right? We have the dotted line right there. We need to calculate this radius to be removed as we move along the axis the entire way. Because that we set up as 20 minus g of x to then remove all of this part from the actual graph. So because of that, the setup is going to be the 20 squared minus 20 minus g of x, all that squared. Okay, so the form integration is correct. The limits are all there, right? And then they want to make sure that the constant, right, the limits and the constant, right, is going to be all there set up as well. Okay, so this is going to give us all 3 to 3 correct for part C, and that should just about do it here. Okay, so looks like we have finished this up entirely with all 9 points correct from question number 6 here. Right, that's 9 out of 9 correct. So from all 6 of these problems, we have missed only 2, right? 2 8 out of 9, so giving us a total of 52 out of 54. If you want to see that percentage-wise, this is going to be 52 over 54, giving us, in percentage-wise, 96.30 if you round it there, percent. Okay. Unfortunately, not exactly perfect, but nonetheless, though, that is going to be the result of our work. Just a reminder, of course, that this test is actually going to take place for the students in 2025, this upcoming Monday. This is actually all curved nationally as well. So again, this raw percentages don't exactly matter so much. They'll just give you the numbers from 1 through 5 as the result of your exam. So hopefully, with all of this finally being the actual conclusion to our full course in calculus, this should be a proper way to send our students off. So again, I did state this at the very end of my last video, but we should be moving on to chemistry sometime next week as we get to our summer session of some nice experiments and things that we can show on this channel moving forth. So, as before, again, thank you all for coming in today. This was quite a good experience going through all these problems online, and to all of our viewers coming in and telling and giving our feedback going through this. So this entire exam packet, again, the entire recording will be set up through our channel. You can go back and watch at any time, and hopefully we can come back next time with some more chemistry this time, as this will really be the conclusion to the AP Calculus section of this channel, with that last video capping things off earlier this week. So once more, thank you everyone once more for coming in today, and we definitely hope to see you in the next time with us going through chemistry. So thank you all, and hope to see you next time.